Atong and Aram are grade 10 students who are currently enrolled in a regular high school in the Philippines. Currently, they are experiencing the blended learning modality because of the pandemic. Atong and Aram really like and enjoy the sciences. Due to the pandemic, however, they are not able to do experiments which they really love. So, they thought that they could enroll in an online class for them to quench their thirst for learning. Checking available online courses, Atong and Aram encountered NRCP's B2B or Back to Basic classes.
Hello learners! I am Malaya and welcome to the Back to Basic or B2B online class. Do you have in mind one or two science topics which seem difficult to understand? Or are you curious about something that you have encountered in your science lab during your face-to-face session?
Good day, Miss Malaya. I am Aram and I am also interested in science-related topics. However, the complexities of earth science interest me more.
Hello, Miss Malaya. My name is Atong, and I have always been fond of science. But I personally think that I still have a lot to learn in physics.
Hello, Atong and Aram. Those are indeed interesting topics. With that, I am confident to say that this class is just right for learners like you. Back to Basic or B2B is an avenue to present difficult theories or science concepts in popular language and in a fun way using videos and infographics for kids, students and teachers, and the general public by NRCP experts and scientists. They would like to inspire you both and your classmates to have greater understanding and appreciation of the importance of basic concepts that may lead to further research or thinking. And guess what? You could be one of them in the future. It is one of the online platforms under the NRCP project, leveraging basic research information translation for empowerment in the regions program, or called as Brighter, to enhance science culture in every Filipino. I would also like you to meet your classmates in this class. We have quite a number of grade 10 students like you who also love science.
Hello guys! I hope we will have a fun learning experience together.
That's right! I hope we will all have a fruitful educational adventure.
Wow! I love our learners' enthusiasm! Now, let me guide you through your panventure in this class. Our lessons in B2B are clustered into 3 parts to complete your panventure. We have review lessons which will cover a special topic on Earth and space for the first quarter, and on a special topic in physics for the second quarter. For the current lesson, B2B will bring you to the world of plants and plant diseases and genomics. These topics must be exciting for you, Atong and Aram, and to your classmates as well. Finally, as an additional feature of B2B, we have advanced lessons for you in preparation for your last quarter. How would you like to hear our scientists talk about computational fluid dynamics and math prod?
This is a dream come true, Miss Malaya. I am sure that we will have a lot of fun in this class.
Alright! I know you are all excited to start.
Indeed, Miss Malaya. I cannot wait to learn from our teachers.
But before anything else, let's meet our scientist teachers in this class. Good day, our dear learners. This is your second week in B2B online class. For a quick recap of our first lesson, scientist teacher Mylene discussed volcanic hazards and the impact of these volcanic hazards to people, property, and environment.
Specifically, you were able to first Identify the different volcanic hazards. Second, describe the different characteristics of various volcano-related hazards. And lastly, explain the dangers of these volcanic hazards. For this episode, our lesson is titled The Electric Motor, Its Physics and Possible Miniaturization. And you will be with our featured scientist, Dr. Ed. Excited much? Then let us meet Scientist Teacher Ed.
Hello, Atong and Aram. Hello, classmates of Atong and Aram. I will be your scientist teacher for today. My name is Eduardo Quansing, and I am a physicist at the University of the Philippines, Los Baños. We have prepared a fun-filled lesson for all of you today. After the lesson, you should be able to describe qualitatively how an electric current around the loop interacts with an external magnetic field, determine the physics behind the workings of an electric motor, and extend your understanding of the electric motor down to the very small sizes of atoms and molecules. Before we begin with the lesson, let's define some terms. Electric current. Electric current is a measure of the net charge that flows through a wire's cross-sectional area per unit time. A magnetic field surrounds a moving charge on a permanent magnet. The presence of this field can be deduced from the magnetic force that other moving charges or permanent magnets experience in the vicinity of the field. A torque applied on an object tries to rotate or twist that object in a certain direction. So let's start with the lesson. Have you ever wondered how an electric fan works? How does electricity make the fan blade rotate? If you look inside an electric fan, you will see a collection of wires and gears and coils. At the heart of this appliance is an electric motor that is responsible for rotating the fan blades. An electric motor can convert electricity into rotational motion. That is, it can transform electric energy into mechanical energy. In this lesson, you will learn about the physics of an electric motor. You will see that the interplay between an electric current flowing around the loop and the magnetic field from a magnet can result in the loop to rotate. We will then extend our understanding of the electric motor down to the world of atoms and molecules and explore whether it is possible to construct a tiny electric motor consisting of just a few molecules. Electric motors are ubiquitous and ever-present in everyday life. If you look around you, you will see many devices containing electric motors. In addition to electric fans, appliances such as washing machines, vacuum cleaners, refrigerators, and air conditioners can contain electric motors to operate. Modern electric vehicles are powered by electric motors rather than an internal combustion engine. Imagine all the wonderful devices that we can make if it's possible to create tiny electric motors the size of a molecule. In this lesson, we will investigate the possibility of constructing tiny molecular-sized electric motors. Let's try to build a DC motor. You will need two metallic paper clips, an electric wire coated with an insulation, a magnet, a battery, either size AA, AAA, or D, and some electrical tape. Make sure that the electrical wire is coated by insulation. It's usually transparent, but you should be able to see it if you look closely. Coil the wire around the battery several times. The more coils you make, the faster your motor will rotate later on. Remove the coiled wire from the battery and then tie the opposing sides. Make sure that the coiled wire is nicely balanced so that it can rotate smoothly when it is attached to the battery. See Figure 1 for reference. Scrape off the insulation at one end of the wire, while scrape off only half of the insulation at the other end. Refer to the figure 2. Bend the paper clips to form similar shapes as in Figure 1. Tape one end of the paper clips to the battery. Place the magnet above or below the battery. Now insert the coiled wire through the paper clips and make sure that it's balanced at the middle. Push the coil slightly to rotate it. The coil will keep on rotating as long as the battery has charge. Congratulations, you now have constructed your own electric motor. Let's try to find out the physics behind the workings of this electric motor that you just made. Laboratory experiments have established that magnetic field surrounds the region around a permanent magnet, as shown in figure 3. This magnetic field would interact with the magnetic fields from other permanent magnets within close proximity. Experiments have also shown that a magnetic field surrounds the region around a loop carrying an electric current, as shown in figure 3. When this loop of current-carrying wire is placed near a permanent magnet, their magnetic fields would interact. What is the nature of their interaction? In mathematical terms, a magnetic field is a vector field. This means that it is a field that has both a magnitude and a direction. For the permanent magnetic field in the region outside it is directed from the North Pole to the South Pole. For the current loop, we can imagine an N pole, a North Pole above the loop, and a South Pole at the bottom of the loop. So do you remember that you have learned about magnets in your previous science classes? The sides of two magnets with opposite poles would attract, while those with the same poles would repel. You can verify this if you have two or more magnets with you. Place them side by side, and you will see that there will be two sides of the two different magnets that will attract, while inverting the orientation of one of the magnets will result in a repulsion. Let's take a closer look at the current carrying loop, which is shown in figure 4. The electric current is represented by I, and its direction around the loop is indicated by the arrows. For a loop of radius r, its area is pi r squared. We can take the product of the current and the area, and call it the loop's magnetic moment mu. We can then assign its direction to be perpendicular to the area enclosed by the loop. There are, however, two possible directions that are perpendicular to the loop's area. That is, the direction pointing upwards and the opposite direction pointing downwards. To remove this ambiguity, we follow the right-hand rule by wrapping the four fingers of a right hand around the direction of the current in the loop, and that is the counterclockwise direction shown in the figure. The resulting direction of the right-hand thumb is the direction that we assign to the loop's magnetic moment mu. This is shown in figure 4. Suppose we place the loop in a region of space where there is a homogeneous magnetic field B pointing directly upwards, as shown in figure 4. What would happen to the loop? Since a current-carrying loop is surrounded by a magnetic field, that magnetic field will interact with the magnetic field already present in the region, and resulting in parts of the loop to be either attracted or repelled by the field. Mathematically, what happens is that the loop experiences a torque, tau, that's called the torque tau, which is actually mu cross B, that physically rotates the loop around a specific axis. Let's first explore the meaning of the mathematical expression tau equal to mu cross B. Shown in figure 5 is a wrench oriented along the vector A that is pointing to the right. We would like to rotate the wrench counterclockwise towards the orientation of vector B. To do so, we apply a torque tau, which is A cross B. Unlike a force that is either a push or a pull, a torque is either a twist or a rotation around an axis. Therefore, when we apply a torque tau, which is mu cross B, on the current carrying loop, we are rotating the loop's magnetic moment from its original orientation into the direction of the magnetic field B. The vector product or vectors mu and B then leads to the torque vector tau. Since torque is a vector, it has a magnitude which we define by tau mu B sine theta, where theta is the angle between mu and B, as shown in figure 4. This magnitude has a maximum value when theta is 90 degrees, since sine 90 degrees is 1, while the sine of the other angles not divisible by 90 degrees is less than 1. This means that the torque is at the strongest value when mu and B are perpendicular. On the other hand, the torque is a minimum when theta is 0 degrees. since sine of 0 degrees is 0. In other words, there is no torque when mu and b are parallel. Since torque is a vector, it must also have a direction. What is its direction? We again follow the right-hand rule to determine the direction of the resulting torque. To do this, first align the four fingers of your right hand along the direction of mu, then curl them towards the direction of b. The resulting perpendicular direction, where the thumb of your right hand points to, is the direction of the torque. What does this direction mean? It indicates that the interaction between the magnetic moment mu of the current loop and the magnetic field is to rotate the loop into an orientation where its magnetic moment is parallel to the magnetic field. If you align the four fingers of your right hand along mu, then the tendency for the loop is to rotate towards the curling your fingers into B, with your thumb pointing along the direction of the torque. The current loop would want to rotate in order to align mu and B. So now that we know what happens when you place a current loop in a magnetic field, wherein the loop's tendency is to rotate because of the torque, let's go back to our setup of the electric motor. Remember the instruction that the wire must be insulated? Your electric motor will not work if the wire is not insulated. Shown in figure 6 are the directions of the current if the wire is insulated, at the left figure, and if the wire is not insulated, the right figure. Notice that a magnetic moment mu appears in the left figure because the current flows in a complete counterclockwise loop, while in the right figure, because the wire is not coated with an insulation, the current can flow as long as there is contact between the parts of the wire. Current will therefore flow to the top and bottom parts of the loop simultaneously until they reach the other side of the loop. A magnetic moment will therefore not appear because the current is not flowing in a complete single loop. In our electric motor setup, the magnet at the bottom provides the magnetic field that interacts with the magnetic moment of the current loop, thereby resulting in a torque that rotates the loop. Consider the two figures in figure 7, illustrating two separate orientations of the loop. In the left figure, the plane of the loop is vertical and the magnetic moment is shown pointing to the right. The magnetic field B from the permanent magnet is directed upwards. The interaction between magnetic moment and the magnetic field results in a torque that tries to rotate the loop in the counterclockwise direction. Now let's take a look at the right figure. The plane of the loop is now horizontal and its magnetic moment is pointing in the same direction as the magnetic field. Since they are parallel, there is no longer any torque that tries to rotate the loop. It is also at this point where the significance of scraping only half of the insulation at one end of the loop plays a role. At this point in the loop's motion, that end of the wire that is insulated is now in contact with the paper clip that is attached to the battery. However, that end is insulated. There is no longer any direct contact between the wire and the paper clip. The electric current will no longer flow. Without a current, there will be no magnetic moment, and without a magnetic moment, there will be no torque to rotate the loop. However, because of inertia, the loop will continue to rotate counterclockwise until the plane of the loop is horizontal again but facing the bottom. At this point, direct contact between the wire and the paper clip returns, and the electric current would again flow. This leads to a magnetic moment that interacts with the magnetic field, resulting in a torque that rotates the loop counterclockwise. The loop therefore continues to rotate counterclockwise as long as the battery is charged. Now that we have learned about the physics of why an electric motor works, let's extend our understanding by applying it to extreme conditions. Let's imagine that we shrink the motor down to very small sizes, about the same size as a large molecule. For example, instead of using a copper wire, we use a long conductive polymer, like for example acetylene, as our conducting wire. We coat the polymer with an insulation, loop it around into a coil, just like what we did before, scrape off the insulation at one end and only half at the other end, apply a magnetic field, then attach a battery. Will we get a molecular size electric motor? It is possible. Imagine the kind of wonderful devices that we can create with such tiny electric motors. We cannot only create tiny molecular-sized electric fans, but we can also use tiny motors as the basis in assembling components for mobile, tiny, nanometer-scale robots or nanobots. Because these nanobots are at the size of molecules, they can be injected into the bloodstream of a person to go on a search and destroy mission, hunting cancer cells, harmful viruses and bacteria, and other foreign substances. Our tiny electric motors can also be used as components in the flight mechanism of nanometer-sized drones, or we call them nanodrones, which can be used to explore and study extreme locations on Earth, such as, for example, inside the volcanic crater or the surrounding area of a radioactive material. We can even imagine sending our tiny electric motors out into space to help in the colonization of other planets and asteroids. There are so many possible applications that we can imagine for our tiny electric motor, but why are we not seeing them now? Are there complications and challenges in creating these tiny molecular-sized electric motors? Yes, that complication is called quantum mechanics. Physicists from the past century learned that the physics of atoms and molecules and electrons and protons is not entirely the same as the physics of everyday objects such as tables, chairs, cars, and airplanes. Let's consider, for example, the hydrogen atom, made up of one proton at the center and one electron orbiting around the proton. The proton is nearly 2,000 times heavier than the electron, and so it essentially just sits there at the middle of the atom where the lightweight electron would zip around. You can visualize the atom to be similar to the solar system, where the proton is like the sun that sits at the center, while the electron is like one of the planets orbiting around the center. It is important to take note, however, that this picture is not entirely correct. Physicists found that it is not possible to accurately locate the position of particles, such as the position of the electron and proton in the atom at any instant of time. And the lighter the particle, the more difficult it will be to exactly pinpoint its location. What we know and calculate for sure, however, are the probable locations where the particle might be. Our theories and equations in quantum mechanics allow us to know only probabilities, not certainties. We therefore have to modify our idea of how an atom looks like. Instead of a proton at the center and an electron moving in a well-defined orbit, what we have is a fuzzy center where the proton likely sits, and even a fuzzier, larger sphere surrounding the center, representing the probable locations where the electron might be found. Is it possible to devise an experiment in the lab that can find exactly where an electron is located? Yes, but every time you repeat this experiment, you will find that the electron is at different locations. The positions with high probability, also the locations where you will most likely find the electron. Although there is also a small chance that the electron will show up at locations where there is low probability. Why can't we know the exact positions of quantum particles? Is it because our theories and equations are not complete, and there are missing terms and effects that are not accounted? Those are good questions to ask, and physicists have been working hard to answer them. What we know so far is that experiments have not found any missing or hidden effects that are not accounted for in our theories, and that our equations are complete. The probabilistic nature of quantum particles is really a part of nature that we cannot remove. How is this quantum fuzziness related to our search for a molecular motor? We have learned that a current-carrying loop of wire in an electric motor rotates because of the interaction of the loop's magnetic moment with the magnetic field, giving rise to a torque that rotates the loop. As we shrink this loop down to molecular sizes, quantum fuzziness shows up, and we lose the exact information of where the electrons that carry the electric current are in the molecular wire. There will be an electric current as long as the two ends of the molecular wire are attached to a battery. However, we will not know exactly how much current will flow across the wire. And we will not know exactly then how much magnetic moment is going to be generated. But what we will know are the average current and the average magnetic moment. In a moving quantum particle such as an electron, we can associate a probability wave that moves with the electron. So just like ripples on the surface of water, such waves have physical properties that are different from particles. For example, waves can experience interference, diffraction, reflection, and transmission through a barrier. The wave property of the electron complicates how we can understand the workings of a motor at the molecular level. In particular, the length of the molecular wire can dictate whether there will be electric current or not across the device. In addition, the interaction between the electrons and their associated probability waves must be considered. These are some of the reasons why the physics of the molecular motor is still not fully understood and an active area of research. Okay, so now it's time to see if you have understood today's lesson. Try answering the following questions to check your understanding. Number 1, which among these appliances do not contain an electric motor? A, electric fan, B, air conditioner, C, refrigerator, or D, none of the above. Number 2, in making your own electric motor, why must you use a wire that is coated with insulation? Letter A, to protect the wire from moisture in the air. Letter B, to minimize friction between the wire and the paper clip. Letter C, to make sure that the current moves in a loop around the wire. Or letter D, to avoid electric shocks. Number 3, why do we fully scrape off the insulation at one end of the wire while only half of the insulation at the other end? Letter A, so that the coiled wire will rotate in only one direction. Letter B, so that the magnetic field is removed during half of the wire's rotation. Letter C, so that the electric current can continuously flow across the wire. Letter D, so that the loop's magnetic moment will not go to zero. Question 4. What is the reason why the loop rotates in the electric motor? Letter A, the battery supplies a force that rotates the loop. Letter B, the electric current around the loop gives rise to a magnetic moment that rotates the loop. Letter C, the magnetic field supplies a force that rotates the loop. Or letter D, the interaction between the loop's magnetic moment and the magnetic field gives rise to a torque that rotates the loop. Question 5. Why is quantum mechanics a challenging complication in realizing molecular motors? Letter A, the positions of quantum particles such as an electron cannot be known exactly. Letter B, the probability waves associated with the electrons in the motor can interfere with each other. Letter C, we cannot exactly calculate and only know the average value of the current flowing across the molecular wire. Letter D, all of the above.
Hello kids! I am Teacher Christine. Thanks for joining us today. Let us give a big hand to Teacher Ed for that very interesting lesson on electric motors. Hi, Teacher Ed.
Hi, Teacher Christine. Thank you. Thank you, everyone, for attending this lecture. I hope you've learned a little bit about the physics of the electric motor and inspired you to delve a little bit deeper into physics and also into quantum mechanics.
Dear students, I'm sure you have some questions for Teacher Ed. If there is something you want to ask about today's lesson, just type in the chat and we'll answer it here. If you want to remain anonymous, you may send your questions via DM. I'll get the ball rolling. Teacher Ed, you demonstrated how a DC motor works. What is the difference between an electric field and a magnetic field?
Yes, that's a good question. An electric field is something that surrounds a charged object. Okay, so if let's say you have an electron surrounding that electron is an electric field, but there is no magnetic field. A magnetic field shows up if you have an electron that is moving, okay? Or if, let's say, you have a permanent magnet. Let's say, for example, you take a magnet, a refrigerator magnet, and then you get another magnet. If you place them together, they would interact. That interaction is due to the magnetic field. An electron, if the electron is just sitting there, just stationary, just sitting at a certain location, if you have a magnet and then you place near that electron will not feel anything, because a magnetic field does not interact with the electric field of the electron. But if the electron starts moving, there is going to be a magnetic field that is going to be produced by the electron, and then you have the magnetic field from the magnet. They would interact. The electron would feel the magnetic field from the permanent magnet. So this way you can differentiate between the electric and the magnetic fields.
Thank you for that answer, Teacher Ed. What does DC mean in your discussion of the DC motor? Are there other types of electric motors?
Yes. So the motor that I've shown earlier in the video, where we have a battery, okay, that is a DC motor. DC means direct current. That means the potential, the voltage. Okay, the battery. When you buy a battery, it says 1.5 volts, 4 volts, 7 volts. That is the potential, the electric potential. And DC means that it is constant, does not change in time. So it's a direct current. The motor uses a battery, and the potential there is constant. It's always, let's say this one is 1.5 volts, so it's always 1.5 volts. There are other motors that do not use a battery like this, okay, but they use, say, electricity from an electrical outlet. We know that electricity from electrical outlet is AC, alternating current. Okay, so if you look at how the electric potential from the electrical outlet behaves, it's going to be like a wave. Okay, it goes up to plus and then minus, plus minus, plus minus. That means it's alternating. So you have an alternating current, and you can still construct a motor using alternating current, but this time you need not just have a coil with what you need is going to be a more complicated setup. Okay, so not just a coil with just a simple coil, okay, that is insulated. Because the AC, the charge is going plus and minus, so you have to consider that, take note of that. And then, but it's still possible to construct a motor from this AC source.
Okay, thank you, Teacher Ed. So now you know what are those numbers in the voltage in your batteries. The next question. What is the difference between force and torque? So you mentioned earlier torque.
Yes. Yeah, so there's a difference between force and torque. They're almost similar, but a force is what you've learned from your science classes. Force is either a push or a pull, right? For example, if you say a refrigerator at home, and then let's say you push your refrigerator, but it's too heavy, you're applying a force. It's a push, okay? Or let's say you pull a box on the floor, okay? So that is also you're applying a force, okay? But the torque is a twisting or a rotating motion, okay? There's still force, but there is going to be a twist, okay? That means, for example, say I have this ball pen, and if I apply a torque, that torque is going to be, you apply a force at one side of the ball pen, and then you hold the other side, and then when you apply that force, that would rotate the ball pen. Okay? So the difference between a force and a torque is that the force is either a push or a pull. It's linear. That means it's either forwards or backwards, a push or a pull. But the torque is rotational. Okay? So paikot, or it's a twist. Okay? That is also a torque. So in our experiment earlier in the video, the magnetic field, the torque is due to the interaction between the magnetic moment and the magnetic field. That would rotate the current carrying loop. That would give you a motor.
Okay, very interesting. So we learned today that the magnetic field provides torque, but we do not see it. It just rotates the wire earlier. The next question. So we have a question here. Can I turn my electric fan into a generator?
Yes. An electric fan uses a motor, right, to produce wind. That means you have a rotating fan. Okay? A generator is the other way around. Okay? So for an electric fan, you use electricity to rotate an object. Okay, to rotate the fan. A generator is the other way around. The generator is you have a rotating object, and that would generate electricity. Okay, so baliktad yung difference between they are inverses. Okay, electric fan and a generator. You can generate electricity using a magnet and something that's rotating. Okay, you can just invert the setup that we've seen in the video. Instead of having a battery, okay, you can put a magnet, and then you have another. You need another rotating magnet. Okay, so you need two magnets. One is supplying the magnetic field, the constant magnetic field, and then another one is rotating. And then you connect a loop. You will generate a current along that loop. Okay, that is how a generator works. For example, for let's say a steam, let's say a geothermal generator, it's the steam that rotates a magnet, okay, and then there's another magnet outside that rotating magnetic field would generate a current. Okay, so to answer your question, yes, you can turn an electric fan into a generator, but you have to invert the process. Okay, so instead of using electricity to produce wind, you use the rotation to produce electricity. Yes.
Thank you for that clarification, Teacher Ed, between the electric fan and a generator. And this is the background of our geothermal plants. Now, the next question, what background do we need if we want to study quantum mechanics?
Okay. So if you are interested in learning more about quantum mechanics is an interesting topic. Okay, so there are still a lot of open questions. There's still a lot of things that we don't really still understand. Okay, when we deal with small particles, okay, electrons, protons, and even collections of these electrons and protons. But what background do you need to start studying quantum mechanics? You will see after high school, you will see that if you go to take, say, a bachelor's degree in physics or applied physics, you will need to take classical mechanics and electrodynamics. Ano yun? Classical mechanics is just the physics of everyday objects. Okay, Newton's laws, for example, the topics that you learn in high school. Force is equal to ma, Newton's second law. If you know that, that is classical mechanics. So the physics of forces, the physics of torque, mass, acceleration, velocity, classical mechanics. And then you need a little bit background in electricity and magnetism, electrodynamics. Okay? So the physics of electric charge, the physics of the magnetic field. And from there, you can start learning quantum mechanics. Also, you will need a little background in math. Okay, so compared to other physics subjects, the math in quantum mechanics is not too difficult. Okay, but you would need to learn, say, how to deal with matrices. Okay, how do you multiply or add matrices? How do you take the eigenvalues? Okay, how do you get the eigenvector? So there's a mathematics requirement to learn quantum mechanics, but you can learn that along the way. Okay. In quantum mechanics, what is more difficult is not the math but the physics. Okay, kasi sometimes the physics is not intuitive. Right? So when you see, for example, let's consider classical mechanics. Okay? When you see a car that is moving, you know exactly what is going to happen. That if it's moving with constant velocity, you would know that after some time it will move, reach a point. But in quantum mechanics, no. Okay, so sometimes you get surprises. Okay, so the physics is not as easy as classical mechanics, but it's also going to be more interesting. Okay.
Thank you, Teacher Ed. So quantum mechanics is probabilistic. So here we have another question. What is the most practical application of quantum mechanics that we might see very soon?
Actually, we're seeing applications of quantum mechanics right now. There are certain materials that are purely quantum. Okay, if we don't have quantum mechanics, these properties will not show up. Like, for example, superconductivity. Okay, so a superconductor is you have a material, walang electrical resistance. You've learned from your physics classes that you have, if you have a wire, copper wire, tapos merong current, there is going to be resistance. That merong resistor, merong resistance, because it is a material. It is, even if it's copper, it's metallic, there is still resistance. But there are certain materials that are superconducting. Superconducting, ibig sabihin, there is no resistance, zero resistance. So you have a wire, a superconducting wire. If you place the current, and then let's say this wire is a loop, you loop it around, then there's current. That current will just flow indefinitely, forever, kasi walang resistance. Okay, so it's a superconductor, does not dissipate. Another property of a superconductor is that it repels magnetic fields. So if you have a superconducting material, tapos mayroong magnetic field, that magnetic field cannot penetrate, so your material can sit on top of the magnetic field. Okay, it looks like it's flying, but it's actually just sitting on top of the magnetic field. Now, these properties are because of quantum mechanics. Okay, there is there's something called the wave function. Okay, so in the interactions between the electrons and the ions in the materials. In the end, what happens is that the wave function is special because of the interactions in such a way that the electrons become superconducting, or the material becomes superconducting. Now, practical applications, you would see that, for example, in maglev trains in Japan, okay, in other countries, they use the superconductors. So they place this, instead of using wheels in the train, they use a superconductor, and then the train would float on the rails. Walang friction, okay, or minimizing friction. That train can travel faster. So that is one practical application. There are many. Okay? I would probably use up one whole day to discuss practical applications, but that is one example.
Thank you, Teacher Ed. So that's why you hear the sound of the LRT and MRT train when they arrive, because there is friction. So what Teacher Ed discussed was that the maglev trains, they have no friction, so they can travel very fast. Thank you for that interesting phenomena, Teacher Ed. So now we have the last question. Why don't we see the effects of quantum mechanics in everyday objects?
Although there are practical applications, we don't see effects like probabilistic nature of materials. Say, like the books behind me, right? Why are they not probabilistic? Or myself, right? Why don't I have a probability wave? Actually, as it turns out, we have probability waves. But the thing is, the probabilities is almost 100%. Okay, that's why you don't see the fuzziness. Okay, that is because there is something called the correspondence principle. Okay, where if you have only one electron, you would see large probabilities. You can there are probabilities, okay, for the location of the electron, for example, and the differences are large. okay, for different locations. But as you add more and more electrons into the system, once you have, say, 1 mole of electrons, 1 mole, ibig sabihin na times 10 to the 23 molecules, okay, times 10 to the 23 atoms. There are many electrons. The system, the probabilities, if you consider the probabilities of all the particles in that system, the system would act like it's classical. That means tanggal na yung probability, almost 100%. It looks like you know exactly nasaan yung system na yan. That is because there are many particles. Okay? So, like me, for example, I have billions, how many moles of molecules in me? So I have a lot of electrons and protons. So probability, although I'm still probabilistic, my probability is almost 100% that I am sitting here. If I were not, I might be, going, I might be facing through my chair or something like that. Okay, but no, you don't see that because there are many particles. Yeah.
Wow, Teacher Ed, that was pretty intense. Not only do we have superconductors, but we are waves. But for now, we are 100% here.
Yes.
So it looks like today's topic is a hit with our students. Teacher Ed, are there any other tips for our students who would like to learn more about today's topic? Last word.
Yeah. You guys are lucky these days because you have the internet. That pwedeng i-Google mo na lang and then see and then look at YouTube videos. So there are a lot of YouTube videos. I've watched YouTube videos as well before I made this lecture. The only thing that I noticed is that the physics is not clearly explained in those YouTube videos. So if you want to supplement what you've learned in this lecture, you can watch those YouTube videos. Okay. You can also start reading books. Okay. If you are really interested in physics, you have a lot of background knowledge to learn. Unlike, for example, in fields like math, where some things are innate. Like, for example, arithmetic, or how do you multiply, how do you add? It's innate. Okay, you don't have to read the book. Okay, or you would be taught, let's say, sandali lang, and then you would know exactly what it means when you add 2 numbers or multiply 2 numbers. But physics, no. Physics is a product of centuries of hard work by really, really smart people. Okay, Newton, Einstein, Feynman, people like that. Okay, so you have no choice. You have to read books, and then you have to learn what they discovered, and then from there build from that. Okay, the important thing is you build a good background first. Okay, before you dip your toes into new things. Okay, but the reward is, in the end, the reward is actually going to be rewarding. Okay, as you would discover new things, discover concepts, discover things about the universe that no one has known before. That is a great high. Okay? If you start discovering new things, it becomes addictive, and then you start keeps on going. You keep on searching for new things, keep on discovering. So build your background first, okay? Yung math, and then yung foundational physics.
Thank you, Teacher Ed, for your sharing your knowledge and experience today. So kids, if you want to know more about his research, Teacher Ed is doing a lot of research on quantum devices. You can just Google it and look for his work. With us now is our B2B Principal Mayet Sumagaysay. Hello, Principal Mayet.
Hello, good morning, Teacher Christine. And thank you, B2B Teacher Ed, for answering the questions so passionately. And of course, Dr. Christine, our other B2B teacher, is also a physicist like Dr. Ed. So my dear students, you want to feel high when you discover, sinabi yun ni Teacher Ed, and yung aha moment when you discover things, and you'll have a lot of that in quantum. So can you also imagine very small motors doing impossible missions inside your body? as mentioned by B2B teacher Ed in his lecture, like searching for the cancer cells, which medical x-rays cannot do, or those small motors being able to assist the surgeon in really getting into the specific damaged genes or selected cells being treated or repaired. Or you have miniaturized motors for yarn winding. Have you ever seen at one time your mom or your grandmother finding it hard to fix tangled threads while sewing? Can a small motor deliver them from the stress? There are a lot of applications of the miniaturized electric motor which may release you from stresses or save energy and costs in production or make a worker more efficient or simply improve the market mechanisms. So will you still need big machines to bring a heavy load from here to there like what conveyors do, or power the movement of farm products from the field to the storage house, or to haul fish catch from the sea to the fish port to the canning factories? Atong and Aram and all of you dear students, as your B2B principal, I would like to guess that while you were listening to B2B scientist teacher Kwan Sing, you were already thinking of other applications of miniaturized motors. I challenge you to keep that inspiration. Keep thinking of a novel use of miniaturized electric motors. You may find it even from your daily routine. What are your needs today? Which ones could most probably be addressed by these wonders in tiny electric motors? I hope that B2B teacher scientist Dr. Ed tickled your minds, your interest and curiosity on the opportunities and surprises that a small and miniaturized electric motor can give you. The miniature motors are getting to be more advanced, and you are in the midst of these advances. To be curious about, to learn, and to experiment, and not to be weakened with the thought that there are computations to make and complications to understand. I am happy to hear the question about what you will need to study, what you will need to prepare in order for you to study quantum mechanics. In the near future, I am expecting some of you to be like Teacher Kwan Sing and Teacher Christine. If you need mentors and inspirations along the way, they are there, and it was mentioned earlier. And as your B2B principal Malaya, the office and our NRCP scientists and experts will be very glad to handhold you. So we also have with us today teachers Paz, Rodney, and Edmond, who will be there to assist you. Our scientists will inspire you more. So again, this has been another exciting day of science for you, Atong, Aram, and your classmates. You may review the lesson in Brighter Commons, answer the quiz again until you get a mastery of the subject matter. Thank you to our grade 10 enrolled students from the St. Genevieve School of Pateros, and to Director Pabalan and Principal Lizardo. See you all again on Monday, same time, 10 a.m. for our third B2B Season 2 class online. May inspirasyon kayo dito sa usaping agham at kultura. Godspeed to all. Back to you, Teacher Christine.
Thank you, Principal Mayet. And with that, we've come to the end of today's class. I'd like to thank our scientist teacher, Teacher Ed Kwan Sing, for today's exciting lesson and discussion. I am Teacher Christine Villagonzalo, and we'll see you next week where our lesson will be on becoming a plant doctor. This is the NRCP, where we bring great ideas to life. Goodbye and thank you.